The current consensus in AI development is that larger context windows solve the problem of agent memory. We see models hitting 200,000 or even 1,000,000 tokens, with the expectation that injecting entire codebases and libraries into a single prompt will produce reliable autonomous behavior. Yet, in production environments, these highly capable models frequently fail. During multi-step, long-horizon tasks, autonomous agents hallucinate their outputs, drop critical constraints, or lose their primary directives. This failure mechanism is context-rot. As the volume of tokens in a context window increases, the model's ability to accurately recall specific information from that context actively degrades. This manifests as a positional bias called the lost-in-the-middle effect. Models reliably execute instructions placed at the very beginning and the very end of a prompt, but they overlook the critical details and rules buried in the center of a massive text block. Expanding the context window creates a bloated, noisy environment, where the agent's core procedural instructions are buried under thousands of tokens of irrelevant conversation history. The architectural constraints of the transformer attention mechanism create the mathematical conditions for context rot. In this grid, we see the n-squared scaling problem. Every new token must compute pairwise relationships with all other tokens. This quadratic scaling creates a finite attention budget. The model's capacity stretches across these connections until the core signal diffuses. As the agent works, it generates a continuous stream of conversation history and raw tool logs. These new tokens deplete the attention budget. The model loses its grip on its procedural constraints and drifts from its objective. Maintaining agent reliability requires dynamic context engineering, surgically managing this finite attention budget so the model only processes the exact tokens it needs for the current step. The common architectural response to context limits is to bolt on a retrieval-augmented generation, or RAG, pipeline. Data represents static semantic facts, like API documentation. State represents exactly where the agent is within a specific workflow at a specific moment in time. Agentic memory must be engineered into a decoupled, purpose-built 4-layer stack to achieve autonomy. This is the foundation of the architecture, a central reasoner node representing the LLM's active cognitive engine. We anchor this with Layer 1, transient session state. Layer 1 operates as short-term working memory. It holds only the immediate API payload, the active variables, or the current conversational turn. Once the immediate action is complete, this data is cleared, preventing it from polluting the wider system. Next, we add Layer 2, semantic facts. This layer handles the enterprise domain knowledge, official documentation, and historical data. The reasoner queries this layer strictly on demand to retrieve static facts when it needs to understand a specific concept. By isolating Layer 1 from Layer 2, the agent's messy, immediate trial and error thoughts do not permanently corrupt its long-term factual knowledge base. Long horizon tasks introduce a different problem. When an agent spends hours auditing a codebase, it generates massive, repetitive logs of tool calls. If left unchecked, these logs consume the remaining context window. We manage this with Layer 3, episodic event history, using structured note-taking and compaction algorithms. Instead of holding raw logs in its active memory, the agent writes persistent summaries of its progress, like an active loop counter or a subtask checklist, to a local file system. This deliberately breaks the cycle of context bloat. Finally, we cap the architecture with Layer 4, procedural logic. Layer 4 is the agent's absolute ground truth. It contains the invariant constraints, architectural decisions, and codebase rules. It is completely separated from searchable data to guarantee these core instructions are never diluted by other inputs. This 4-layer stack addresses cognitive drift by keeping the context window surgically clean. However, even perfect memory doesn't protect the infrastructure from application crashes or the agent making a destructive decision. Knowing how an agent remembers is only half the architecture. The other half is how it executes. Traditional prompt chains force execution along a rigid, linear path. Standard chatbots take a single prompt and generate a single output. Agents have to reason, invoke external tools, evaluate the result, and loop back to try again if an action fails. When a linear chain hits an unexpected obstacle, the workflow breaks. The necessity for error recovery leads to a shift towards cyclic state graphs. Inside a graph framework, the reasoner node can decide to call a tool, transition to an executor node, receive an error message, and then dynamically loop back to the reasoner to formulate a different strategy. Cyclic graphs give agents the structural freedom to self-correct. We replace brittle if-else logic with dynamic outcome-based routing. To make the system reliable enough for enterprise production, we need a mechanism to persist the exact state of the agent across all 4 memory layers during these complex graph loops. This is achieved using ACID-compliant database checkpointers, like PostgreSQL, integrated directly into the agentic framework. Every single time the agent transitions state between nodes in the graph, a permanent snapshot is committed to the database. These continuous snapshots enable an operational feature known as time travel. Consider a production scenario. An agent hallucinates and executes a destructive action 3 hours into a massive workflow. With checkpointers active, the system halts, and the state rewinds backward to a safe node. Because the state is perfectly persisted, human engineers can pause the workflow, rewind to that safe node, modify a variable, and fork the execution path. The agent resumes its work without losing the progress of the entire run. Constructing reliable AI in 2026 relies on engineering context through memory tiering and orchestrating lifecycle through robust, checkpointed state machines.